I think we can start. The speaker of today is Lukas Zenger, and he will speak about intuitionistic modal logic with the master modality. Please.
Yeah, thank you. So this is joint work with Liede Vogenholz from the University of Amsterdam and Bahare Afshari and Graham Lee from the University of Gothenburg. And it is part of this is published and other parts are still ongoing work. Essentially, what we're looking at here is an intuitionistic modal logic. Now that can mean a lot of things because the literature on intuitionistic modal logic is rather chaotic, but I'm going to explain later more what I exactly understand here as intuitionistic modal logic. But then not just intuitionistic modal logic, but one extended with a greatest fixed point operator, which is called the master modality. This is essentially a reflexive transitive closure operator, also known as common knowledge. Now, our main contribution that I'm going to talk about here in this talk is the development of a cyclic proof system for this logic, which has some nice properties. First of all, it's going to be a very simple proof system, so we don't need any complicated structure on sequence. That is, we can work with plain sequence. Additionally, the system is modular in the sense that we can easily extend it to also account for frame conditions and various classes of Kripke models. And the proofs, so the completeness proof in particular, is also modular in the sense that we can use the same strategy for all these different classes of frames when we prove completeness. In fact, as you will see in the completeness proof, we only have to adapt a very small thing in the completeness proof to gain completeness for a different class of models. And of course, sometimes we have to add a rule. Now, the plan of the talk is I'm going to start introducing this logic, and then the main part will be talking about these cyclic proof systems and also non-well-founded proof systems. How familiar are you with these concepts? I know that Vlad is rather familiar with it, of course. Otherwise, I assume you've heard of it, right? So, okay, I'm going to maybe say a small amount, but then I'm not going to give too much introduction to it. All right. Let's start with intuitionistic modal logic with the master modality. So what you see here is the syntax of our language. We essentially have intuitionistic propositional logic, and then we have two modalities, a box, which is a normal box operator, and the box star, which we call the master modality. Importantly, we don't have the diamond in the language, and in the intuitionistic setting, the box and the diamond are not interdefined. So this is really a diamond-free version of intuitionistic modal logic. When it comes to evaluating, we will start with a very simple class of Kripke models, just bi-relation Kripke models, which is a tuple consisting of a non-empty set of states, a partial order on this set of states, a binary relation on W, and evaluation function, which is, as it is standard in intuitionistic logic, monotone with respect to the partial order. So whenever Fs, well, S is smaller or equal to T, then V of S is a subset of V T. Now, if you're familiar with intuitionistic modal logic, then you might notice that we do not have any confluence properties here in these semantics. Usually, what one looks at is some form of interaction between the intuitionistic partial order and the modal accessibility relation. But for now, we do not have any of this interaction in the logic. When it comes to evaluating formulas, the conjunction, disjunction is evaluated in the standard way. So is the implication, but it's a standard intuitionistic implication. So A implies B is true at a world S, if and only if for all worlds T above S, the classical implication holds. And for the modalities, we have to do something similar in order to ensure that our logic is monotone. So the formula box A at world S is true, if and only for every world T, such that S R tilde T holds, A is true at T. And what is this R tilde? Well, it's just the composition of the smaller equal relation and the modal accessibility relation. So in fact, what we're doing is, in order to evaluate the box form at S, we look at all the worlds above S and then evaluate the box operated there classically. The same thing happens with the box star, just that here we take the reflexive transitive closure of this R star relation. So in fact, we're looking at paths that are like staircase paths. If we're at the current world, we look at every world which is reachable by going up over the intuitionistic order and then taking a modal step, going up again, taking a modal step, etc. So every world reachable like that, A has to be true in order that box star A is true at S. This semantic works well for intuitionistic logic. In fact, we can prove the monotonicity lemma. If S is smaller t and S satisfies A, then T will satisfy A as well. In particular, the monotonicity is really just built into semantics. So for these cases here, we won't even need the induction hypothesis if we prove this lemma. All right, so this is the most basic class of Kripke models that we're looking at. They are nice, but the semantic clauses are not particularly easy to work with, especially for the master modality. So let us look at a subclass of these models which satisfy a certain confluence properties. And we call these models triangle models. These are birelational models which satisfy triangle confluence, namely whenever W is smaller or equal V, and V sees a world U over the modal accessibility relation, then W already sees this world U as well. So in a diagram, this looks like a triangle, therefore we use the name triangle confluence. The dashed line here means that stipulates the existence of this modal relation. These triangle models, they're useful because for them we can use the classical truth conditions and we still obtain the monotonicity lemma. So in fact, we define a second truth relation, which I index here with a little t. And now we can use the classical truth condition. So box A holds in every world which is reachable from S over an R step, then A must hold in such a world. And R star, box star is now just a reflexive transitive closure of R. Interestingly, and in fact this is already known in the literature, if we have such a triangle model, a world and a formula, then if we use the birelational truth condition for any formula, we get the same as if we use the triangle truth condition. So in fact, on triangle models, these two truth conditions, they coincide with one another. And this is easy to see because in a triangle model, the modal relation R is exactly this R tilde, and therefore we get the result for free. This, of course, also means that the logic that we get when we evaluate this language over triangle models contains all the validities of the logic over birelational models. So in fact, the logic over birelational models is contained in the logic over triangle models. Now, we have a sound and complete axiomatization for this logic, which is quite a simple one. All we need is intuitionistic tautologies and then one axiom for the box, the standard K axiom. We don't need any other axioms for box. So if you're familiar with intuitionistic modal logic, what we have here really is the modal logic CK or little ik, the box fragment of this logic. We don't have the stronger logics like capital Ik from Simpson. Additionally, we need fixed point axioms for the master modality. And of course, we need an induction rule for the master modality to capture all the validities and the monotonicity rule. And we can then show that this axiom system is sound and complete. In particular, the completeness proof proceeds via relatively standard canonical model construction, basically combining ideas from the completeness proof for intuitionistic logic and the completeness proof for common knowledge logic. I would like to mention that after I've proven this completeness result, I noticed that a similar axiomatization for a multimodal version of this logic has already been given in the PhD thesis of Michel Marty in 2017. The axiomatization is not quite the same, but the completeness proof is really like the same idea. So this is not a new result, but it is nice to see that there is a simple Hilbert-style system for this. And of course, the completeness is with respect to triangle models. So we have a completeness result for that. Now, I would like to introduce one more class of birelational models, namely so-called functional models. And these are just birelational models where the modal accessibility relation is a partial function. Now, these functional models is in a way the origin of this work. Originally, I was introduced to look at, or I was interested to look at intuitionistic temporal logic, where we do not have any confluence properties for the temporal accessibility relation. And if you do that, then you end up with these functional models. Technically, you would like to have a total function, but for simplicity, let's look at partial functions for now. And here, when we evaluate formulas, of course, we need to use the standard birelational truth conditions by looking at all the worlds above. All right, but evaluating the language over this function model gives an interpretation as an intuitionistic temporal logic, where the box becomes a next operator and the box star becomes a henceforth. Good. So let us denote the three logics that we have now by IMK. This is the set of valid formulas over birelational models. IMF, the set of valid formulas over functional models. And IMT, the set of valid formulas over triangles. Now, we already know that IMK is a subset of IMT, and of course, also IMK is a subset of IMF, since every functional model is in particular birelational model. However, as it turns out, the other inclusions hold as well. So in fact, we get the exact same logic when we evaluate formulas over either of these three classes of models. I would like to mention that the equality between IMK and IMF that was already known since like 20 years, I think, and is in fact very trivial. If you have any birelation model, then this induces in a truth-preserving way a triangle model by just looking at this and using the other truth conditions. So it's very simple to translate birelation models into triangle models that satisfy the same formula. And the other way, of course, from our lemma, we know is already the case. So the equality between IMK and IMT is already known. But as far as I know, the equality that our logic cannot distinguish between arbitrary birelational models and functional models is a new result. The way we established this originally was with using proof theory. Namely, we defined a cyclic calculus for IMK and then showed that we can easily also get completeness of this calculus with respect to functional. And how this works, I would like to show you. So maybe as a quick introduction, as I mentioned before, the master modality is the greatest fixed point operator. Namely, it's the greatest fixed point of this propositional function, which sends P to A and box P. And therefore, as we've already seen in the Hilbert-style system, if we want to design a proof system, we will require some form of an induction rule to capture this master modality. This works well in a Hilbert-style proof system, but in a Gensen-style sequent calculus, using induction rules has some problems. The main problem is that usually when you add an induction rule to sequence calculus, the system is no longer analytic. One way to get around this is to, instead of looking at induction systems, looking at non-well-founded systems. So a non-well-founded proof is a proof in our sequence calculus which admits infinitely long branches. This is essentially a formal counterpart of a proof by infinite descent. Now, proofs by infinite descents are equally strong as proofs by induction. So when we use non-well-founded proofs, we can get rid of the induction rule to still get completeness for our inductive systems. Of course, this comes with the problem of then turning our proofs into infinite objects, which has its own downsides. So, but as I said, it allows us to get rid of the induction rule, and therefore we will obtain an analytic calculus. Of course, we cannot allow any form of infinite branches in our proofs. That is, what we need to do is we need to impose something we call a global soundness criterion on these infinite branches, which distinguishes valid infinitary reasoning from invalid infinitary reasoning. What this global soundness criterion is depends a lot on the logic that we're looking at. The general idea is that we need to have some progress going on, some positive progress in these infinite branches. Okay, so this is the basic idea of non-well-founded proofs. We get an analytic calculus, but of course, as I said, the problem is that our proofs are now infinite objects, and we want to repair this problem. And the answer to that is cyclic proofs. So a cyclic proof is essentially a regular non-well-founded proof, regular in the sense that there are only finitely many subtrees, distinct subtrees up to isomorphism. If you have such a regular proof, then we can present them as a finite tree with back edges, where basically when we've encountered all these distinct finite subtrees, we can start drawing loops by saying, like, from here you can just go back to a subtree that we've already encountered. Thus, such a cyclic proof can be presented as a finite tree, even though it is in fact a non-well-founded tree. And so we can repair the problem of having proofs as infinite objects. Similar, like non-well-founded proofs have to satisfy a global soundness criterion on these non-well-founded branches, the cyclic proofs have to satisfy a local soundness criterion on the cycles, with the idea that if you unfold these cycles back into a non-well-founded proof, then we will get the global soundness criterion out of the local one. I would also like to mention that not every complete non-well-founded calculus is complete with respect to regular proofs. So in fact, there are examples where it is not possible to turn a non-well-founded proof system into a cyclic one. But in our case, this would be possible in a quite straightforward way. All right, so let me introduce the proof system that we use for this logic with the master modality. First of all, we have to talk about annotated formulas because our cyclic calculus will make use of a so-called focus annotation. This focus annotation is used to ensure that we can write down a local soundness criterion in a sound way. So it will be important for the soundness of the system. I'm not going to talk much about the soundness. So these annotations, they are not going to play a big part in this talk, but I would still like to introduce them just for the completeness of this talk. By the way, if you have questions, you can always interrupt about these things. Okay. So an annotated formula is simply a tuple consisting of a formula and an annotation, this little a, which is either u or f. and U means that the formula is unfocused, and if the annotation is F, then it means that the formula is in focus. And we usually write them by a to the power of the small a. A sequence is then an expression of the form gamma arrow delta, where gamma and delta are finite sets of annotated formulas, and the sequence must satisfy some additional properties. First of all, we want that every formula on the left-hand side of the sequence is unfocused. Then we want that at most one formula on the right-hand side is in focus. And if a formula is in focus, then this formula must be of the form box star B or box star B for some formula B. No other formula can be in focus. The interpretation of a sequence is then completely standard. The minus here means that we're just deleting the annotations. So in particular, these annotations, they're syntactic tools. They do not bear any semantic meanings. All right. So here are the rules of the calculus, at least the first page. What you see here is just the rule for the Boolean connectives. And in fact, here the annotations do not play a role. So you can just ignore them. They're always unfocused. And what you see here, this is a standard multi-conclusion sequence calculus for intuitionistic logic. The only perhaps interesting rule here is the implication right rule, where you see that reading top down, we're weakening, we have a single conclusion premise and we're weakening it with a side sequence delta. Or if you read it bottom up, then the delta gets deleted. This is, of course, to ensure that the law of excluded middle cannot be derived in this calculus. Then, more interestingly, we have the modal rules. And first of all, maybe let's look at the rules for the box star. These are standard unfolding rules, as you see them often in the modal mu calculus. So the master modality satisfies the equivalent that box star A is equivalent to A and box star A. And we're calling this formula here the unfolding of the box star A formula. So what these rules here really do is they're just taking, if you read them bottom up, they're just taking a master modality formula and they're unfolding it into its equivalent formulation. Also directly applying the conjunction rule. So box star A, we're getting A and we're getting box star A. On the right-hand side, the same happens. Now here the annotations play a role because this formula here might be either unfocused or in focus. And what happens is, if we move to the left premise, then here we just have the formula A, and this formula is always unfocused. So if we move to the left, we lose focus in case this formula is in focus. But if we go to the right, which is box star A, the focus is kept. And if the formula is unfocused, then of course it just remains unfocused in both premises. Right? So here the focus plays a role. Additionally, we have this box rule here, which is a standard box rule, as you see it in classical logic, just that there is no diamond in the language, which makes it look a bit weird. But essentially, once again, reading bottom up, if you have a box A formula on the right, you can apply the rule, and you delete everything on the right, apart from the box A, and everything on the left, which doesn't have a box in front of it. So box gamma is just a set of formulas which have a box in front of it. Once again, if this formula is in focus, then the focus is kept. Finally, we have two rules to govern the focus annotations. And this rule here is written a bit in a weird way. Basically, if you read it bottom up, here you have a formula in focus, so you can apply the unfocus rule, which just changes the focus annotation to unfocused. And the focus rule does the opposite. If you have a formula which is unfocused and you apply it bottom up, then you obtain a formula which is in focus. So this just allows us to put formulas in and out of focus. All right, so this is the rules of our calculus. And let us now first define what a non-well-founded proof is. First of all, a derivation, which is not a proof, in this calculus of a sequence sigma is a finite or an infinite tree whose nodes are labeled according to the rules that I've just shown you. And of course, the root must be labeled by sigma. So here is an example of a derivation of the sequence box star A, arrow, box star A or B. Once again, if you read it bottom up at the beginning, this is unfocused. So what we can do, for example, is we put it in focus, and then we apply the box star left rule, unfolding the box star formula here. Then we apply the box star right rule, which makes the tree split into two branches. Now here on the right-hand side, we end up in an axiom. But here on the right-hand side, we apply the box rule, and now we're basically back at this node here, right? So this is labeled by the same sequence. So I just put 3 dots on top of it to say like, okay, we're just going to keep doing the same steps that brought us from here to here over and over, generating an infinite tree. The next example here shows that not every infinite branch is good. So this here is a derivation of the sequence box star A, arrow, the set. And what we're doing is we're just applying the box star left rule and then the box rule, and we've hit a repetition. So we can do that over and over again, creating a derivation with one infinite branch. But clearly, this derivation cannot be a proof because box star A, arrow, the empty set is not valid in our logic. So not every infinite branch is true. Therefore, to define what a proof is, we have to say what is this global soundness condition on the branches. And it is defined as follows. A non-well-founded proof of a sequence sigma is a derivation of the sequence such that every leaf is labeled by an axiom and every infinite branch has a good suffix rho prime. This means that every sequence in rho prime must have a formula in focus, and additionally, rho prime must pass through infinitely many applications of this box star right rule, where the principal formula is in focus. So this is this good condition, and in fact, passing through the box star right rule is where what I called before progress happens in our system. Observe that if every sequence in rho prime has a formula in focus, then always the same formula must be in focus. We can't change the focus from one formula to another one, because this would force us here to go through an unfocused rule, and then we would have one sequence which doesn't have a form in focus. So in fact, in such a good suffix, we just trace one formula and its development through that branch. So once again, the previous derivation is in fact a proof. We have this tree which has one infinite branch going always to the right and infinitely many finite branches, which follows this branch here and then eventually goes here to the left. These finite branches, they all end in this axiom here. And the infinite branch has in fact a good suffix, namely, for example, starting from this node here, we have here a formula in focus, and this formula in focus stays in focus for the rest of the branch, and we're passing infinitely often through the box star right rule, where the formula in focus is the principal formula of this application. So in fact, this is a proof. While the previous example here is not a proof because we never have such a good suffix. All right, so this is the idea of the non-well-founded calculus. Maybe one comment here. Usually when you see non-well-founded calculi, you see a more complicated notion of global soundness criteria, using some form of new traces. We don't need to talk about traces here, because the way we set up the non-well-founded system is that it is particularly easy to turn it into a cyclic system. So in fact, the non-well-founded proofs here are almost regular already. And therefore, we can work with these focus annotations directly in the non-well-founded calculus, even though we don't need the annotation for the non-well-founded proofs. We only need them for the cyclic proofs. But we add them in to get this like simple global soundness criterion, which then helps us to get a much simpler proof of turning the non-well-founded proofs into cyclic ones. All right. So a cyclic derivation, we call the cyclic calculus CIM, is just a non-well-founded derivation which is finite. Then we have to define this local soundness criterion on the cycles. And for that, we need a few definitions. First of all, a path through a cyclic derivation is simply a finite sequence of nodes which goes through the path. So in particular, we're not looking at paths that goes through the cycles. We're just looking at paths that start somewhere in the derivation and end the leaf. We then call such a path successful if the following holds. Every sequent in the path has a formula in focus, and the path passes through at least one instance of the box-star right rule where the principal formula is in focus. So this is essentially just a finite version of this good suffix. Given such a derivation, a repetition is then a pair of nodes in the derivation uv, such that there exists a path from u to v, and both nodes are labeled by the same sequence. Finally, a repetition is then called successful if the path from u to v is successful. And this is going to be our cycle. So you can see that if we have such a successful repetition, and then we unfold this repetition into an infinite branch, then the local soundness criterion will give us that this infinite branch is going to satisfy the global soundness criterion as well. Therefore, a cyclic proof of a sequence sigma is a derivation such that every leaf is either labeled by an axiom, or there exists a node CL such that CLL is a successful repetition. Here's once again the previous example. In fact, what I've shown you before, if you just delete the 3 dots, you get a cyclic proof of this sequence. Namely, here we have one leaf which is an axiom, and for this leaf here we can just add a cycle from here back down here, and this is now going to be a successful repetition. These two sequence nodes are labeled by the same sequence. There's always a formula in focus, and we pass through the box-star right rule with the formula in focus. So this is a cyclic proof. As you can see, our non-well-founded and cyclic proofs are very similar. All right.
Yeah, sorry, probably I just don't get something, but Jay, I mean, this condition on non-well-founded proofs is that for every path, for every infinite branch of the proof, something should happen.
Yes.
But here the condition looks like different. Maybe it's actually entails this and then, but it's not immediately obvious to me. It's because now what you're saying that okay, basically okay, you have this finite finite tree, and then you kind of loop it back.
Yes. Yes.
How okay? This kind of what this tells me that indeed. So for basically that this kind of good paths, so do not say infinite branches that satisfy this condition should be dense.
Yes.
But does it also? But what you need
Yeah,
is not that they're just dense. You need that all of them satisfy.
What about the zigzag paths, right?
Yeah,
so if you have like a cycle here,
yes,
and you have a cycle here,
yes,
then in the non-well-founded you will create paths like this, right? Which go like once over here and then once over here.
okay.
And this is of course not directly covered, right? So our local soundness criterion is going to guarantee that the paths that always go left have a good suffix, and they're guaranteed that the paths that always go right have a good suffix.
Mm-hmm.
So what happens if we have this zigzag? And this is exactly where the focus annotations play the crucial role. Because what we have to guarantee is that we're following some formula here. And then when we go to the right, we have to keep following the same formula. And this is guaranteed because here we can only have one formula in focus and we cannot lose the focus. So the formula that is in focus here, let's call it box star phi, must be the same formula that is in focus here.
Okay.
Right? Because otherwise, there would be two formulas in focus in this sequence here. And this is going to guarantee that here we're tracing the same formula. And therefore, these other paths that we can generate by unfolding, they still have a good trace.
Okay.
Right. So this is why the annotations are crucial for soundness of the cyclic calculus. In fact, if we just take the annotations away, then you can create counter examples of soundness by exactly this construction.
Okay.
Which doesn't mean I'm not sure whether you cannot set up a cyclic calculus without the annotation. But if you set it up like we do here, you need the annotation. Otherwise, it's not sound.
Right, but I guess the difference will be that you simply will have to have more complex conditions of what it means for final treatment here.
Yes, I mean there is one trivial way to say like, okay, every path going through a finite proof to a cyclic proof, like also those passes that can loop back, must have a good suffix. But then you just have non-well-founded proofs, right? Then you don't really gain the finiteness. Because here the condition whether a finite tree is a proof can be checked in finite time, because you just have to look at
No, I think actually people usually get around this by referring to results from automata theory, because I mean it's known that that you actually this is a decidable problem, right?
Yes, you can use some tree automata and their finite word problem. Yes, but I prefer if you can just check it directly on the proof instead of having to go to some automata. Or the idea of cyclic is that you can check it directly on the proof. Otherwise, you just look at non-well-founded proofs if you want to use automata.
Yeah, I mean, still, okay, we give it still some final calculation on the proof, but it's very complex calculation.
Okay, yeah, fair. All right, so here is the first result. This calculus is sound with respect to the class of birelational Pripke models, and therefore it's also going to be sound with respect to the classes of functional and of triangle Pripke models. So in order to show that the logic over all these three classes is the same, it remains to show that the calculus is complete with respect to triangle models and with respect to functional models. So let's look how we can do that. When it comes to proving completeness, what we're doing here is we will first prove completeness of the non-well-founded calculus, and then we will show how to turn non-well-founded proofs into cyclic proofs. And the method that we're using for the non-well-founded calculus is to use a proof search argument. So the idea is that given a sequence, we will make a somewhat intelligent search whether this sequence has a proof. And this search will result in what we call a proof search tree. This is essentially a very large infinite tree in which we can find subtrees where we try out all the different possibilities in a reasonable way how to find a proof of this sequence. We can then define a an infinite two-player game on this proof search tree, where the proof search tree forms the arena, and this game is played between prover and refuter. So the intuition should be clear. If prover has a winning strategy in this game, then the strategy tree of this winning strategy should correspond to a subtree of our proof search tree, which happens to be a proof of the sequence at the root. On the other hand, if refuter has a winning strategy, then its strategy tree is an other subtree of the proof search tree from which we should be able to read off a counter model for this sequence. So that is the basic idea. Completeness then follows from the fact that this two-player game is determined. So one of the two players has a winning strategy, and therefore each sequence we will either get a proof or a counter model for the sequence. Now, importantly, the way we are going to set up this proof search tree is going to be crucial in the question what kind of counter model we can get. And I'm going to say more about that later, but the main thing here is that we only need very small changes in the proof search tree to obtain counter models of different form. And therefore, this approach is very modular. It can be easily adapted to obtain different counter models without altering the overall argument that we're using. Good, but let's talk about how to set up this proof search tree. First of all, quickly remember the rules of our calculus. If you look at them, then you see that all these rules are in fact invertible, apart from two exceptions. The implication right rule is not invertible because we're deleting the side set of formulas delta here. And also the box rule here is not invertible due to the same reason. Now, having non-invertible rules is not very good for proof search. Because if you think about it, if you start with a sequence that you want to prove, as long as you apply invertible rules to it, nothing can go wrong. If the sequence is provable and you apply invertible rules, then whatever you get remains provable. However, once you start applying non-invertible rules, you might apply them in the wrong order or to the wrong formula. And then what happens is that suddenly you go from a provable sequence to an unprovable sequence. So this is something that we want to avoid happening. And therefore, the general strategy, which is usually used in proof search argument, is to delay the application of non-invertible rules as long as possible. The idea is we start with the sequence at the root, and we're going to apply non-invertible rule as long as we can. That is, until applying invertible rules doesn't add anything new to the sequence. And then once we're there, we have to start applying the non-invertible rules. And there is where we have to make a choice. First of all, we call sequence where applying invertible rules does not result in anything new. We call them saturated. I'm not going to give you the precise definition, but that is the intuition. We apply invertible rules as long as we can, and eventually we reach a saturated sequence. We can then define a proof search tree as follows. First of all, fix some inference rule C. This is a new inference rule which doesn't occur in our calculus, and this C rule stands for choice. The idea is that this C rule is going to collapse every possible application of non-invertible rules into one rule. And the shape of the C rule is going to be crucial in obtaining different forms of counter model. We are then going to build the proof search tree for a sequence sigma as follows. First of all, the root is of course labeled by sigma. We then want that every invertible rule is applied preservingly. What does that mean? It means that if you read the rule bottom up, the principal formula is also going to be a side formula in the premise. Right? So if you have a formula A and B in the conclusion and you apply the conjunction rule, then we're just assuming that A and B also occurs in the premise. So we're not losing these formulas. So we're applying these invertible rules preservingly, meaning that every time we apply an invertible rule, there are more formulas in the sequence than before. Then no invertible rule is applied to a sequence in which the principal formula is already saturated, meaning that if you have a sequence, for example, where you have A and B on the left, but you also already have A and B present, then we're no longer going to apply the conjunction rule here because we wouldn't gain anything new. Here we would just get the same sequence once again. A node is then a leaf if and only if it is labeled by an axiom or by a saturated sequence to which the C rule cannot be applied. And the C rule, which I'm going to define later, can only be applied to saturated sequence. So this is maybe a bit a lot of clauses. The basic idea is we put the sequence sigma at the root and we start applying invertible rules until we have reached in every leaf an axiom or a saturated sequence, which will eventually happen. And then we're going to apply this choice rule, which is the merging of the non-invertible rules to this saturated sequence, which will give us a lot of new premises, which are in general not saturated anymore. And then we're just going to repeat the procedure of applying invertible rules and then applying the choice rule again, then applying the invertible rules again, thereby creating such an infinite tree. All right. The crucial thing is this choice rule. Depending on how we define the choice rule, we can get different countermodels from such a proof search tree. So let us first look at the simple case, the choice rule for triangle models. In fact, this choice rule can also be used to get countermodels which are just birelation. What you see here is on the bottom, here in the conclusion, this is assumed to be a saturated sequence, right? And we have some formulas here, pi, we have some formulas with boxes, and we have some side formulas, sigma. And then the interesting formulas here are the implications and the box formulas on the right, because these formulas cannot be broken down any further without applying a non-invertible rule. So these are the crucial formulas of this choice rule. Now, what the choice rule does here in the simple case is it simply applies every possible combination of an implication right rule or a box rule to this sequence all at once. So we're getting a lot of premises. For example, this premise here is obtained by applying the implication right rule to the formula A0 implies B0 here on the right. Similarly, this one here is obtained by applying the implication right rule to the formula AL implies BL here. And similarly, we're getting all these modal premises which are obtained by applying the box rule to one of these modal formulas here. So applying box rule here deletes the side sequence and deletes the boxes in front of it. So this choice rule here has a lot of premises for every formula that we have here. And of course, these sequences are in general not saturated anymore. So we have to start applying invertible rules to them once again, etc. Also, some things happen with the focus annotations, but that's not so important right now. So just ignore the focus annotations here. Good. So this is a very simple version that's just like blindly apply any possible rule applications that you can apply at the same time. All right. So before I'm going to show you how to obtain a counter model for that, now let me quickly tell you how the game works now. If we define a proof search tree with such a choice rule, then we define a game, infinite game between prover and refuter as follows. Basically, a play corresponds to a branch of T. Each sequence in our proof search tree will either be a position for refuter or for prover, and what they can do in such a position is choose the next node above. So go from the conclusion of a rule to a premise of the rule. That's their choices. So a play will correspond to a branch of the tree reading bottom up. And all the invertible rules are going to be refuter choices. That is to think as follows. If we are at an invertible rule, then refuter has to say, well, which of the premises are not provable for prover, right? And he goes there. While prover in an invertible rule must have an answer for any premise of the rule. But when we're at a choice rule, then there are a lot of non-invertible rule applications to choose from, and there not every position might be provable. So it is in fact prover who has to say which of the premises is still provable, and refuter has to answer to it. So the choice rule is a prover choice, and every other rule is a refuter choice. Prover then wins a play if the corresponding branch ends in an axiom or is infinite and has a good suffix, and otherwise refuter wins. You can then show that this game is determined, that is exactly one of the two players has a winning strategy for any proof search tree given some choice rule. And you can also show directly that the winning strategy of a prover corresponds to a proof of sigma. So you just look at the strategy tree that results from all the plays occurring in a winning strategy, and this is trivially going to be a proof. On the other hand, the winning strategy of refuter corresponds to what we call a refutation. And this is defined as follows. And this is just like reading off the possible plays that can occur when refuter follows his winning strategy. So, of course, a refutation must contain the root because every play starts in the root. There cannot be a leap, which is an axiom. Right? Otherwise, it would be a winning play for prover. No infinite branch of a refutation can have a good suffix. Otherwise, this would be, once again, a win for prover. Then, if a refutation contains a node U that is labeled by the conclusion of a choice rule application, then the refutation must contain all premises of that rule as well, because this is a prover choice. Whatever prover does there, refuter must have an answer. And similarly, if the refutation contains a node that is labeled by any other rule, that is any invertible rule, this is going to be refuter choices, so there is going to be exactly one premise of that contained in the refutation. So in fact, our refutations are going to look something like that. We have the sequence sigma at the root, and then we have a single branch that goes up until we reach a saturated sequence, and then we're going to have all these different premises of the choice rule, which then result in a single branch once again, etc. In fact, here I made a simple example where we only have two implications and one box rule. Now, to read off a counter model here, what we want to do is we will collapse an entire branch that leads from the roots to the first conclusion of a C rule application into one world of our model. And this world should falsify this saturated sequence here. Observe that this saturated sequence extends sigma, so if it falsifies this sequence, it's also going to falsify sigma. Now, this means that we have to satisfy everything that occurs on the left, and we have to falsify everything that occurs on the right. In particular, we have to falsify these implications, and intuitionistically, that means we have to create a new world above the current world, satisfying the antecedent and falsifying the consequence of this implication. And this can be done by looking at these left premises that are obtained from applying implication right rules, right? So this premise here corresponds to applied implication right rule to this formula. And now what we have here is that A0 is on the left and B0 is on the right. So intuitively, this will falsify this implication. Therefore, the branch here that goes up until we reach the next saturated sequence is going to be a new world that is going to be above the current world in the intuitionistic order. And the same we can do here. Finally, for the modalities, we say that each application of a modal rule, the premise that corresponds to it, will give us a new modal successor. Right. So by doing that, what we get here, we have to falsify box C. Well, this branch here will correspond to a new world, which is a modal successor of the current world, and it will falsify C. Of course, this just gives us an arbitrary birelational model. So in order to get a triangle model, we then have to use the trick here to just take the composition of smaller equivalent R to obtain a triangle model falsifying the sequence. So a bit more formally, we can define the canonical model that is based on a refutation as follows, and observe that this definition is very general. It has nothing to do with the specific choice rule it has. In fact, we can use it later to also obtain different countermodels. So the set of worlds is just the refutation modulo, the equivalence class, which identifies two nodes of the refutation if and only if there is a path in between them which doesn't go through any instance of the C rule. So that's the idea of collapsing all these worlds into one. Then we define this one-step smaller equal relation, which is exactly what I said. A world is smaller than another world if the world corresponds to the conclusion of a choice rule and the other world corresponds to the premise to an implication premise of that choice rule. And then, of course, we have to take the reflexive transitive closure of that. Similarly with the modal relation. So whenever we have the conclusion of a choice rule, then we relate the modal relation and then we just close it on the triangle confluence. And the evaluation is just by looking at the saturated sequence, the left-hand side, and just take any proposition that occurs there to say these propositions are true at that world. And this, in fact, will give us here a triangle model that will falsify the sequent at the root if it has a refutation. So in that way, we obtain that our calculus is complete with respect to the class of triangles. Now, when it comes to functional models, the only thing in this whole construction we have to change is the choice rule. And in fact, we can use this choice rule here. So if you think about the construction of the counter model, if we have our refutation, goes here from sigma, and then here we have a choice rule with multiple conclusions, then, well, we want to collapse this into one world. And now the problem we have here is we might have multiple box formulas which have to be falsified, but we can only create one modal successor to the current world. So we can only falsify one of these formulas and not all. So what we have to do is we have to delay the choice of building a new world to falsify these modal formulas on the right to a later point, right? So the idea is here, if we have all these modal formulas, we pick one of them to create our modal successor and falsify this formula. And then we add in this sequent here. And basically, this sequent is just going to be the exact same sequent as down here. Ignore the subscript for now. This is just going to be the same, so it's going to be saturated, and which means we immediately apply another choice rule. And we will then treat this sequent here simply as an intuitionistic successor of the current world. So basically, we add in a copy of the current world above, which then can be used to falsify another modal formula, and then we just continue. Of course, we have to be a bit careful, because if we're adding here a copy of the current world, then we're also going to have to falsify all the formulas that we have to falsify here, right? So maybe here we have an implication formula, which we falsify here. So we will also going to have to add in the world above here. Additionally, if we falsify the formula box phi 1 here, and now here we're falsifying the formula box phi 2, we still have the formula box phi 1 in the sequence. So we also going to have to falsify box phi 1 again up here. And this is what this subscript is doing here. I'm not going to give the detail, but the idea is that we're just rotating through. We're starting falsifying the first formula, we add a copy, we falsify the second formula, we add a copy, until we falsify all formulas, and then we just have to start again, falsifying the first. So in fact, we're going to build an infinite tree here, or an infinite intuitionistic tree, which keeps falsifying these box formulas. But now, if we do this, then you can see that we're in fact getting a functional counter model from such a choice rule, right? Because now each world here will only have one or at most one modal successor, and therefore we're going to get a function. In fact, if you want to show that functional models and birelational models give the same logic semantically, you can also do a model construction where you show how to translate a functional model into a birelational model. And the model construction uses the similar trick, right? It takes the functional model and then it starts adding worlds above, adding intuitionistic worlds as well. So this is really also the reason why the logic cannot distinguish between these between these classes of models. All right, so this gives us that we are complete with respect to the class of functional models, and therefore that these three logics are in fact identical. How much time do I have?
I think so.
20 minutes.
I think basically around 0 minutes.
0 minutes.
Okay. We start at 1:30, so we have a.
No, but yeah. No, okay. I think we started with around 11:40. But actually, kind of the idea for the seminar is that people either give blank or talk, which is
Okay. I see. Okay.
Right.
The slides is 1 hour long.
Okay.
Yeah, out of time.
Then give me 4 more minutes and I'm
Okay.
done. I'm just going to summarize some additional results because I mentioned something about the modularity of that. So let me quickly mention that. Oh, yes. First of all, we can now turn this non-well-founded proof into cyclic proofs. And okay, let's not go through the proof. It's very simple. Basically, just take the non-well-founded proof and prune it in each branch at the first successful repetition. It's going to do the trick. Because of the way we set up the non-well-founded proofs, we don't need any automata here or anything. So in fact, we're getting that we have a cyclic calculus which is complete with respect to all three classes of models. Now, one mention, usually in intuitionistic logic, you're working with single conclusion calculi. We used multi-conclusion calculi here because that is easier to do proof search with. But in fact, this is not a restriction. We have shown how to translate the non-well-founded and the cyclic calculus into single conclusion calculus by a recursive co-recursive translation. So we also get complete single conclusion calculi. The completeness of the Hilbert-style system that I've shown you at the beginning gives us the finite model property, and therefore we also obtain a decidability of checking validity. And in fact, using the cyclic system, we can translate this into a parity game and show that checking validity has an exponential upper bound. What the lower bound is at the moment is something I'm working on. I think the validity checking problem is x time complete, but I have yet to show the x time hardness of this. But it's not that bad, especially if you compare it with these modal fixed point, intuitionistic modal fixed point logics that have confluence properties. There, the complexity is much worse.
I know, just was curious why precisely getting X time rather than piece space in this kind of that's more usual for model logics, but
Yeah, I don't think it's in piece space.
okay.
Yeah, because of the master modality. I mean, classical master modality is also exponentially.
Yeah, no, what I mean is that the piece space typically corresponds to a situation where you can do this proof search.
Yeah.
When you can do proof search, essentially kind of staying within the class of subform or something like this.
Right.
But okay, so it's really not the case here.
I'm not sure. I don't think it is. But maybe we can talk afterwards. Otherwise, I'm taking time to.
Okay.
Yeah. Okay. Now, one comment here. We can easily adapt this calculus to account for serial birelational models where every world has at least one modal successor. For that, we just replace the box rule by this box S rule, which can also be applied if there is no box formula on the right. So delta 0 here is a singleton set or empty. And then the whole proof search argument can be done the same. The only thing we have to adjust is the C rule for functional models but it's really trivial because you just apply the box rule with the box S rule, and you're immediately getting completeness for serial models. In fact, what we're getting is completeness for total functional models. And hence we can also conclude that the logic does not distinguish between serial, birelational, and total functional models. And this now gives us an interpretation of this logic as a form of linear time temporal logic when we evaluate it over total functional models. However, this is a very weak version of linear time temporal logic. For example, some typical temporal topologies, like in the next step A or B implies in the next step A or in the next step B, is not valid in this setting. Additionally, we can also consider this logic as a common knowledge logic. Namely, Zenger and Marty have introduced in 2016 a version of intuitionistic common knowledge logic, which is formulated in essentially the same way as we did it here, just that we have multiple box operators for multiple modalities. And in this setting, the box star then becomes the common knowledge operator, right? So it's a version of intuitionistic common knowledge. They provided a finitary sequence calculus with an induction rule for this logic. And they also showed that they can capture the logic over reflexive and S4 models. Here they use triangle models, right? So a reflexive and S4 triangle models. However, their calculus is not analytic. They use unrestricted cut. Now, we can improve on their results. Namely, we can easily adapt our calculus to a polymodal language by just introducing box rules for each agent and adapting the master modality rules. And then we can get the same way completeness for this multimodal language by just adapting the choice rule once again. Additionally, we can also account for reflexive and S4 models by adding the corresponding rules to our calculus. And then in the case of reflexive models, we don't need to do anything in the completeness proof. We just get the completeness for free. And in the case of the S4 models, we have to adapt the choice rule once again, and we get completeness. So what?
Yes, sir, when I'm talking about a multimodal case, do you mean that you have single master modality or multiple master modality?
One master modality, which is the reflexive transitive closure of the union of all the boxes.
Okay,
right?
okay.
So just the common knowledge.
Yeah,
Standard, yeah. So once again, our methods for proving completeness are quite robust for different frameworks. Of course, this leaves the question, what about S5? Because common knowledge is usually interpreted over S5 models. Now, Zenger and Marty left this open as a question. And in fact, I've recently solved this, but I don't think I have time to go into that. So the very short version, when you add S5, the logic becomes pretty weird because the S5 relation together with the triangle confluence starts interacting in a weird way. Mostly what you get is if you have a world and above it you have a world, right? Then this world sees itself by reflexivity, and therefore by triangle confluence, the world below also sees it, but by symmetry, the world above also sees the world below. So what you're getting then is that the box starts behaving like a classical modality. In particular, things like box P or not box P becomes valid in this logic, even though the law of excluded middle does in general not hold. And to deal with that, we need different techniques to get completeness. We can still use the same calculus, we just have to adapt it with some additional rules for the reflexive and the S5 case, as well as this weird rule for the interaction between implication and box. Basically, this says that whenever you have an implication where the antecedent is a boxed formula, this implication is a classical implication. Now, if we also add cut, we can prove completeness. In fact, we can prove analytic completeness by restricting the cut to analytic cuts. So we still get an analytic sequence calculus for S5, intuitionistic master modality. But we use different techniques now. The proof search doesn't work anymore in that way. So you can establish it by a canonical model construction where you make important use of the cyclic proofs to prove the truth level. All right. So I'm not going to go further into that, but that's just as a side comment. It gets interesting when it's S5. Then thank you very much for your attention.
Are there any questions?
Okay, so you didn't include the diamonds,
Diamond is not included.
but
No.
in the total functional models, the diamond would be the same as the box.
Yes,
Right.
yes. The box and diamond collapse into the
Yeah.
next operator. Yeah.
Can you, in that situation, add a star version of the diamond?
Yeah, that should be possible. Yeah, in the total function case, yes.
Yeah.
But that might become then a different logic. It might no longer be the case that you get the same logic if you evaluate it over birelated or over total function models. I'm not sure, but that would be my intuition. So you could make a weak version of intuitionistic temporal logic that we have considered. So without the frame conditions, that would work.
And do you think these techniques would work?
I think so. Yeah, I think that the techniques work. It's really a matter of once you start adding confluence properties, the whole thing becomes much more difficult.
Yeah, coming back to complexity. So, what do you think is what kind of upper bound can you prove?
Upper bound exponential.
So, is it? Sorry. So you know that it's inside of us.
I know it's in X time, yeah, but I don't know whether it's below somewhere.
Okay. Okay. Sorry. Yeah. Yeah. Okay. So kind of. So how you do, because I think kind of naively I see how you can achieve, I think, non-deterministic X time.
I'm using a technique of translating the cyclic calculus into a parity game. So I'm basically defining a cyclic parity game, right, where the players apply rules and choose premises of the rules. And by doing that, building like a cyclic proof.
Yes.
And this parity game requires three priorities, essentially, like to get, and then you can prove that something has like the proof as a winning strategy if and only if as a memoryless winning strategy if and only if there is a cyclic proof for that sequence.
Yes.
And then I'm using complexity results about parity games. So there is a result proven in 2017, which basically, if the number of priorities is constant, then the game can be solved in polynomial time in the size of the arena. And the size of the arena is going to be exponential in the size of our sequence. And with that, I'm getting an exponential upper bound.
Okay.
But there might be much more. I'm not familiar very much with complexity, so there might be like a more direct ways to analyze.
Yeah, no, I think kind of at least kind of at least direct. I think the kind of direct approach simply gives NX time.
Okay.
Because the next time simply respond to indeed you can bow simply doing say to search for cyclic proofs or more precisely to calculate them.
Yeah.
Then okay, you indeed like this the kind basically the size of the set of sequences exponential.
Yeah.
And then you simply need to arrange them in this graph. And I think kind of problematic part is kind of making these backlinks really.
Okay. Yeah.
Because of course like this kind of, and this is kind of naively gives time, but yeah, okay, but yeah,
I see.
Of course,
Yeah.
But okay, so. But no, what I'm kind of bit strange here because the kind of X time is somewhat weird bound for this kind of search algorithms.
You think so?
Yeah, no, I mean, I think kind of kind of special things that are more like either non-deterministic, kind of time,
Right.
or classes, or indeed, say, space.
Key
So
space,
very
yeah,
elsewhere in natural class for this kind of problems.
Right.
I
Yeah.
don't I don't know. I will have to say.
Yeah.
But Jay, I think there are even that many X time complete problems.
Yes, I'm not so surprised because the classical version of common knowledge logic is X time complete.
Oh, it is. Okay.
And in
Oh,
fact, we can our logic is not that much different from it.
oh,
It's
okay,
just,
okay. Then again,
yeah.
no, we have that.
So that's why I'm thinking that it's also X time.
No, I mean, if you kind of know some similar result
Yeah.
situation where I think, then okay.
In fact, the way I think I want to prove the hardness is by double negation translation from the classical
I see.
into the intuitionistic case, but there's some work to do because I have to extend it to the modality.
Okay.
So, but that is the hope that this works.
Okay.
To get the volume. So.
Are there any other questions?
Questions online?
No. Thanks.
Oh, okay.
Okay.
Thank you. Again.